Hi, so let's go ahead and look at the energy equation, right? So we were basically looking at the energy equation, of course, and we wrote down that rate of change of total energy is a sum of the heat flux and power, right? So we looked at a fluid element, right, and we've got an expression for this q dot. Okay, now let us look at the other two and how we're going to do anything about them. Okay, so this is where we had stopped last time. Okay, so let us look at the the total now energy. Let us look at total energy. Okay, so that we can find an expression for the left hand side. Now total energy is equal to internal energy, right, plus kinetic energy plus potential energy. Is that right? So let's call this as, so therefore if I take, this is an elemental element of the total energy, right? So I need to sort of integrate this. Okay, so I take this is the energy in a small volume or small fluid element, right? So therefore I write dET. Okay, right. So dET, right? So total energy, okay, is equal to, okay, so is equal to internal energy, which is an elemental mass, right, into E. So this is usually internal energy per unit mass. So I think this is also something I've talked about right at the beginning, right? So so internal energy, so dm into this, right, plus ke is half m v square, okay, and this we're going to write as elemental mass into, so this is basically a potential function. Okay, so this is a potential function, and it's a steady sort of potential function. Okay, so this is okay. So, or if I were to write this, is equal to, okay, I'm going to break this mass up and say this is equal to this density into volume, right, into E, right, plus half rho into, again, dV v square, right, plus rho dV and psi. Okay, so I can write this as rho dV, okay, I can write that as E plus half v square plus psi, right. So this is what we can sort of write this as, and I can also sort of say that this bit, so let's see, we can also say that if I were to write this, and I can write this whole as a total energy per unit mass, so I can write this, or say total, yes, so I can write this in this fashion. I can also write this as rho dV small et. Okay, so that is essentially this part. So then I can, I'm going to sort of work this. Right, so I'm going to call this as 4. So we get this expression. So now we, however, have to find out det dt, right? So we need to find out the rate of change of the total energy. Okay, so rate of change of total energy is equal to rho dV ddt, okay, of E plus half V squared plus chi. Is that right? And this. Okay, so therefore you can see that I can actually write out the left hand side of the energy equation in something like 5. Okay. Now next thing is, let us go ahead and again look at W, right. Now again writing out W. So now work done, I mean work done on a fluid element. What is your idea of work done on a fluid element, right? So far we have been talking about drag, right. We said one of the reasons to study boundary layers, the velocity boundary layers, is because the viscosity is dominant, right, and it exerts a certain pull, right, on the body on which it has developed. Fluid is on which it has developed. Fluid is trying to move over a body, right, and it faces a certain resistance, and this resistance is from the fluid, and this is due to the viscosity of the fluid. And if you kind of make a sum of that on the total surface area, right, of the fluid which is experiencing that, it essentially develops into the expression for drag. So that's what drag is all about. And if you are going to make a fluid flow happen, right, you will have to encounter the drag, otherwise it's going to be pulled back and flow is yes, it's going to be retarded, right. Okay, so therefore if from that context one can understand that, and we also talked about the shear stress, right. So we said we calculated coefficient of skin friction, right, and we calculated in terms of the wall shear stress. So therefore what we are doing now is going right near the wall and looking at taking a fluid element, right, taking a fluid element, taking a small little fluid and see that how exactly, what is going on with that, right. So when I say work done, I basically mean therefore, so if when it is like applying due to the viscosity, right, it does apply a resistive force, so which comes out to be shear stress. Now the fluid is in layers, right, and it shears off, right. So I'm talking about a fluid element, right. So then there is a certain shear stress which it is experiencing, right. So of course I'm so the normal forces, right, let me sort of write this here. So I'm going to say this is the normal force in the x direction, So see if this makes any sense. This is kind of undergrad knowledge, so I'm not going to repeat that, but if you find it a little more not very easy to understand, do let me know, maybe I'll kind of elaborate on this part. Okay, so because I think this is something you may have done right around in the first years of your engineering program. Okay, so write this plus right into sigma x plus this, right. Right. So It's not very difficult to understand from here, I hope, because what we are basically saying is that you have, like I've shown qx here coming in, right. So this also has a velocity, right. So this also has a velocity, right, which is here, and the sigma is basically the normal force, right. So when that, so sigma x, basically sigma in the x direction. So now when that happens, so this is on the left face, right, and so I mean the way I am calculating the work done in the sigma x for sigma in the x direction. Okay. So for sigma in the, so this is the for sigma in the x direction. Now so like we did qx on the left boundary is just qx, and what is the flux which is leaving from the face EFGH, right, across dx. So that is again qx plus this. Now similarly you have u, right, here into sigma x, right, u into sigma x on the left hand side, and on the right hand side, see u also changes, right. So u also changes by u plus, similarly del u del x into dx, right, that is the u which has changed, right, into the same change in sigma x, which is again sigma x plus del sigma x del x into dx, and then we multiply this by the area across which it is leaving. So we get something like that. Okay. So that's what that's how we are calculating, you know, the power or rate of work done. Okay. So if I do that, so you can probably see here. So if I do this, minus u sigma x plus, so I'm going to multiply that, u sigma x plus u del sigma x del x dx plus sigma x del u del x dx plus del u del x del sigma x del x dx square, right, all of that into dy dz. So if you see this, I should be able to, these two sort of cancel each other out, right, and I'm also going to take dx out of the bracket. So then what I get, so this is equal to u, right, plus sigma x, right. And also if you look at this, right, we have a square of dx, which is anyway small, and we have a multiplication of two derivatives. So we in all likeness can, you know, ignore this. So these sort of, you know, that can be ignored. Okay, it's very small compared to these. So then that term goes. So what I have is volume. Okay, so if I write this this way, right? So therefore, so this is right. So you can see that I can also sort of write this the term inside the bracket, okay, as this, right. Is del del x of u sigma x into this. Okay. So if I do that, okay, so this is nothing but, what does this term even mean? It is the rate of work done, right, by normal force sigma in the x direction, right, in the x direction on the volume dV. So let me sort of write that down. What this means, you know, what this means is the rate of work done, okay, by the normal force sigma in the x direction, right, on volume dV, right. So, therefore, so now that we have done this, so we shall now write it down for total why total force, total rate of work done by all the forces is nothing but, so we will sum that up. So, that plus in the y direction and z direction. So, it will be, yeah, well, I am not writing an extra step. So, w dot sigma x plus w dot sigma y plus w dot sigma z, right. So, here, so this is essentially, I can say it is divergence, okay, of sigma into the velocity vector for this. Okay. So, if I do that, this is this. Okay. So, therefore, now we can sort of write down, okay, the energy equation in the following way. So, we can now write down the energy equation going back. So, therefore, the energy equation which we had here basically. So, we called it something, yeah. So, this is the equation that I am talking about now. Okay. So, let us see, we have got an expression here in 3, right. We got an expression here in 5 and we have got an expression here in 6. Let us put all this together and see what we get. Okay. So, okay. So, let us write that down. So, let us look at 5. So, what we are going to write here is rho d dt right, this is equal to, we had q dot, right, which is minus divergence q dv, right. Divergence sigma this, right. So, let us take out, let us take out the dv throughout, right. So, let us take that out. So, if I do that, so I am not going to erase it just to sort of, so we can take that out, cancel sort of throughout. Okay. So, then so the left hand side, okay, left hand side is the total change in energies that you can see, internal energy, kinetic energy and potential energy, right. This is the total change in energy, right. Right hand side is energy supplied due to, so energy supply, so here this is the, this term, right. So, this is the energy supplied, right, and I do not know if you have noticed, but when we first started out, we said that we are going to assume that heat is going to be transferred through the walls, right. It is going to be transferred through the walls. I have probably not mentioned that. So, I have not written it, but I did sort of mention that. So, what I mean by that is that heat is going to be, there is a way in which you can transfer the heat. So, this is by conduction, right, conduction. So, this is the left hand side is total change in energies. So, the second term here is on the right hand side, this term is basically the energy supplied due to conduction, and this is the work done by surface forces, right. Now, so to do a little bit of sort of math, okay, if I were to do this bit of math, and so we will say that the stress tensor sigma, right, and the viscous stress tensor tau are related. Okay. So, we kind of just write it like that. So, stress tensor this, okay, and viscous stress tensor right, viscous stress tensor is equal to tau, okay, and this, then these are related as sigma this. It is rated as sigma is equal to minus a P, and what is P? P is just the pressure, right? P is the pressure. Okay. So, therefore, okay, so this is the equation. Let me sort of write this out, you know. So, what we get, so therefore, what we get from here is rho ddt this this, okay. Okay. So, and this we are going to call as 7. Is that right? Okay. Now, so from this equation, from 7, right, from 7 what we can now write is that ddt, right, of so we can write the left hand side like this, right, because we've written earlier that this is the total energy, and I can write that as small e t, right, and I took the rho inside. So, therefore, I am writing it in this fashion, right. Did I mention, I think I wrote that the total energy E t, yeah. So, from 4 you see we did sort of write that, okay. Okay, so if I write that, that is equal. No, let's keep that equation. Yeah. So then on the right hand side, from here I can write minus divergence Q minus rho v. You're right. Okay. And we've also said that sigma is equal to minus p plus tau. So therefore we can also write this as minus divergence Q minus p plus tau this. Is that right? So, again divergence, this is Q, okay, plus this minus this. Okay. So, now I am going to expand again the left hand side, okay, left hand side, and write that down as del del t of that, okay, plus gradient, right. So, this is nothing but the total derivative. So, I am sort of breaking that down. So, this is instantaneous and this is the convective change, right, in the total energy. rho AT, okay, that is equal to divergence. So I'm going to just write that down. This, right? Now if you right, so I'm not expanding this part. I hope you kind of get it, right? If you don't realize how I got, this, right? Just drop me a note and I will explain that. Okay. Okay. So now what I'm going to do is I do this, right? Now this v dot the grad, okay? So if I write it like this, so essentially I can write this, okay? This term, I can write this term as nothing but divergence of rho Et v, right? I can write it like this. So therefore, right? Therefore, the above equation, therefore del del T is equal to minus divergence Q okay sorry minus tau v, right, plus this, okay. This, okay. So let me put this in sort of bracket. Okay, so I am essentially taking this to the right hand side. Okay, so yes, so I do intend that to be negative. That is going to be sort of negative, right? Okay, so okay, yes, fine. Okay, so once so therefore now I'm going to just sort of rearrange this a little bit and write it that delta, this thing, is rho Et, okay, is equal to minus the divergence, okay, of, here I'll take the common, V common, so P plus rho Et V, right, minus that, okay. Okay, and this is, I'm going to call that the equation, right? So if I if I did that, okay, now we slowly sort of getting to a place where we are introducing new stuff here, okay. Now you see, so we've got the total energy term in here, the pressure term here, shear stress here, and heat flux factor here. Now we also know the total enthalpy is also connected to the energy, pressure, and density, right? So if I do that, then rho dt, right, is equal to, well, d dt of that, right, plus d dt of P. So I took the rho and multiplied throughout, so I will need a rho here, okay. So this is what it is, okay. Now if you look at this term here, okay, the last term, which is essentially the total derivative of the pressure. So what I will get here is, so this term actually, so what I get is, this is going to boil down to del T plus grad P, right? So what I can get is del P del T plus grad of, right? And therefore we can get this as divergence of PV, right? So this is nothing, so total derivative is nothing but divergence of PV. So therefore I can write this as, so therefore I can write the here this term equation, I can write that, okay. Okay, so that is something, and we can also, as we have seen here in this equation, in equation 8, that del T of rho E T, we can also write that as a divergence, right, given by equation 8 here, right. So if I'm actually missing a particular step, but I think you can do that there. So rho, right, is equal to divergence Q, okay, plus divergence tau V, okay, plus del P del T. Now if you see from equation 8, we've got this term. So the second term is divergence of tau V, which is what we got here. This term is minus divergence of Q, which we got here. Okay. We also get minus divergence of PV, right, which will cancel out with this divergence of PV, which we get from this term, right. And the next one is minus divergence of rho ET V, right, which is minus divergence of rho ET into V. So which is what we are kind of using here. Okay. Okay. So once we, so this is so okay. Let us sort of mark that. Let us mark that. Okay, and we're going to mark that here. Okay. So well, fine. So now having come here, okay. So let us see. Let us look at this now. Equation 7 is here. Okay, if you see equation 7, right? If you see that, now from 7 I can basically write. I can basically write. I'm going to separate this. I'm going to separate this part, the internal energy and the kinetic and potential energies. If I'm going to separate that, then I can write, right? So then I can write, so let's just say, so from 7, right, what we can write is rho dE dt plus rho ddt of half v squared plus psi, right, which is equal to minus divergence of Q. Okay, let's look at this equation here. So minus divergence of Q plus divergence of rho v. That, right? Now let's call that as 1, right? Now for Navier-Stokes, from the Navier-Stokes equation, okay, rho ddt okay, is equal to grad P plus divergence of tau. Okay. Now, I am going to call this as 2, and like I said, the detailed derivations is something that I will post for you, so that you kind of have a feel for it. Okay. Now, using 1 and 2, what we will get, okay, right. So, let me just sort of write that and close this. So, using, if I do this, then what I get is rho d e dt, which is okay, minus grad p, right, plus that divergence tau is equal to minus divergence q plus divergence this, okay, or rho dE dt is equal to gradient P minus divergence Q minus V divergence tau. Divergence tau. Okay. Now, if we use 1 and 2, okay, if we use 1 and 2, we get this expression, right. So, then and we use the expression Q, which is equal to minus thermal conductivity grad temperature, right. If we get this, we will get equations 1 and 2, right. So, if we use 1, 2 and this relation, what we essentially get is equations 1 and 2, right. So, right. So, essentially once we come here, we basically realize that it is possible to solve for the temperature field provided the velocity field is known, right. So, based on that, okay, so based on that, what we will do is we will write down the equation using the similarity variable, so that we can also solve for this in the solve for the temperature field of a given boundary layer. Okay, so we will stop here and do a little bit of this in the next couple of modules and see that what kind of things that we look what kind of things we will get, and how the equations shape up, right, and is there like a physical thing that some physical inferences that we can actually make from the equations that we will we are kind of near that, and if at all we can make a simple enough calculation, simple solution to get the temperature flow field in a for a boundary layer case. Okay, so we'll stop here. Thanks.